So with this, we've finished the aerodynamic model of a sounding rocket. So now what we're going to do is we're going to try to see what's behind these equations, all right? And before going into a deep analytical analysis of stability, which is what we're going to start doing in the next video, I'm going to give a simple example of something we can extract from these equations, which would be calculating the maximum allowable wind the rocket could withstand. So imagine the rocket is flying vertically, and if it finds a perturbation, then a corrective moment is going to try to let's take other colors. It's getting ugly. A corrective moment is going to try to stabilize the rocket. However, this corrective moment will decrease in function of alpha. This means that if this is alpha and this is the corrective moment, at alpha equals 0 or at around alpha equals 0, we'll have a certain moment m, which is negative, by the way, because it's trying to decrease the angle of attack. However, as alpha increases, you can check that the corrective moment is going to increase, well, decrease in an absolute value, but it's going to decrease in a sense that every time as we increase alpha, the corrective moment is going to be lower, up to a point in which the aerodynamic center is on top of the center of gravity, thus the corrective moment equals 0. And this is what we're going to call alpha limit. What I'm describing here is actually something that is buried inside the equations I presented to you before. You can see this by just the equations describe all this behavior, okay? So at this point, at this alpha limit, there will no longer be a corrective moment. And by the way, this alpha limit is function of the geometry, but also the flight, let's say the flight conditions. This means that it's going to vary along the flight. It's not going to be constant. So we can make a case in which we have a vertical rocket, and suddenly, well, a vertical rocket that is flying at a velocity v. So the rocket feels a wind of magnitude v, and suddenly it finds itself with a wind w, a crosswind. So the rocket, which was flying vertically and at an angle of attack 0, suddenly it's going to find itself at an angle of attack alpha. And the tangent of alpha equals w over v. If we substitute alpha for the alpha limit, we could find, let's put it this way, tangent of alpha times v. If we put alpha limit here, we could know the maximum crosswind, or the crosswind that would cause the rocket to become unstable at a given flight velocity. If we found velocity in terms of height, if we did a trajectory simulation, we could then know the maximum allowable wind in function of the height. So we could know that if they gave us a wind profile in function of altitude, we can know if, well, it's too high, or it's good enough for the rocket not to destabilize. Of course, this is a simplified. We've made the simplification that, well, the rocket was actually flying straight, and it suddenly finds a crosswind. But still, it could be useful, for example, for determining the maximum crosswind just out the launch tower, because indeed the rocket will be flying vertically, and suddenly it will find itself an angle of attack change. So this was just a simple demonstration of, what's behind the equations. And on the next video, we're going to go deeper in, stability of the rocket.